Okay, so what we're going to look at today is we're going to look at building on some of the integration by inspection that we had a look at last week. And just look at kind of how we can apply similar principles just in slightly more, with slightly more complicated functions. Now it's really useful for us to think about differentiation first. So we've done loads of stuff on the chain rule during lockdown. We've done a bit of a recap on that since we come back. So what we're going to do is we're just going to start off by differentiating both of these using the chain rule. Okay. So looking at this first one, when I start to differentiate this one, okay, what I'm going to do is I'm going to identify what my big function is, my outer function. So my big outer function there is just 2 lots of something cubed. Okay, so when I differentiate 2 lots of something cubed, I'm going to bring the 3 down to the front, so it's going to become 6. I'm going to leave my inner function alone. And then I'm going to subtract 1 off the power. Okay. Then what I need to think about is, well, what do I need to multiply that by? Well, I need to multiply that by the derivative of the inner function. Now my inner function is this part here, so I just need to multiply that by the derivative of 3x squared plus x, which is going to be 6x plus 1. Okay. Now if we just tidy that up slightly, what we get is we get 6 lots of 6x plus 1, 3x squared plus x all squared. Okay. Now what we want to think about is, what form is this written in? Now if we let this inner function, which has been preserved from our original function to our derivative, if we call this f of x, because that's kind of the thing that links the two, we can see that the form of our function here is f of x being raised to a power, and then in front of it I've got the derivative of this inner function being multiplied by a constant. So what we've got is we've got this form k f dash of x, f of x to the power of n. Okay, so let's see what happens if we do one with a bit of trig involved. Now this one, okay, we need to identify that we're going to use the chain rule first of all. What I would do, just to make things look a little bit clearer, is just to remember that sine x to the 5 means the whole of sine x all to the power of 5. Okay, so then if we start differentiating this using the chain rule, because we've got a function inside a function, what we're going to do is, if I kind of look at my big function first of all, well, my big function is just something to the power of 5, and when I differentiate something to the power of 5, I get 5 lots of that something, so I'm leaving the inner function alone, to the power of 4. So it's literally bringing the 5 down, I've still got the power of 4, and then need to remember to multiply that by the derivative of the inner function. So our inner function in this case is sine of x, and when we differentiate sine of x, we get cosine of x. So again, we can just tidy that up a little bit. And when we tidy that up, we're going to get 5 cos x, and then we're going to have sine x to the power of 4. Okay. Now again, if we have a look at kind of where we started and where we've ended up, the thing that's been preserved, the thing that they've got in common is this sine x, which we can call our inner function. So we'll just call that f of x. And then if we look at the general form of what we've got here, we've got our inner function being raised to a power, and then in front of it, I've got a derivative of that inner function and a constant. So we can see that although I've got one involving polynomials here and another one involving trigonometry, they both give me the same form. And these are both functions that have been differentiated using the chain rule. So what we want to be able to do is we need to take a function that looks like this, identify it as something that's been differentiated using the chain rule, and then reverse that process so we're then able to integrate it. So what we want to be able to do, if I just kind of split this up and kind of reverse what we're going to do now, we want to be able to integrate something that is written in this form. Because if we can identify something's being written in that form, and we know there's a set of steps we can use to kind of reverse this process, then we can integrate something that's written in this form. Okay. Now, if we think about reversing the steps here, what's happened each time is the power's been reduced by 1. Okay, so 5 to 4, 3 to 2. Okay, and we've multiplied by the derivative of the inner function. So if we reverse those steps, what we're going to end up doing is we're going to end up leaving everything as it is, but we're going to increase the power by 1. Okay, and then we're going to divide by this new power. And if we think about what we were doing here, we ended up multiplying by the derivative of the inner function. So to reverse that, we also need to be dividing by the derivative of the inner function. And then when we try this kind of idea, what we should be, hopefully what will happen, these two things are constants, which will just tidy each other up, but we should end up cancelling down at some point. Okay, so if I show you how that works in practice by just integrating our answers from this first part and seeing that hopefully we get back to the original functions. So let's just have a go at that. So if we take, let's start off with this one. Okay, so if we start off with this one here, we've got 5 cos x sin x to the power of 4 dx. Okay, so applying this principle up here, what we're going to do is we're going to leave everything alone. The only thing we're going to change is we're going to increase the power by 1. I'm then going to divide that by this new power, multiplied by the derivative of the inner function. Now the derivative of sine is cosine. And then we mustn't forget our constant of integration. Then what happens is the cosine x's cancel, the 5's cancel, so we can see our answer is just sine x to the power of 5 plus c. Well, that's what we started with. We differentiated using that, differentiated this using the chain rule. We've reversed that, integration by inspection, or reverse chain rule if you like, to get back to this. Okay, what we've done is we've added 1 to the power, we've divided by the new power, multiplied by the derivative of the inner function. So let's just check this one as well. So again, we're going to start off with our answer and show that if we use this method, it gets us back to that. So what we've got is we've got 6 lots of 6x plus 1 and 3x squared plus x squared dx. Okay. What we're going to do is we're going to leave everything alone. The only thing we're going to change at the moment is adding 1 to that power. Adding 1 to the power, I get 3, and then we divide by the new power, multiplied by the derivative of our inner function. Now the derivative of 3x squared plus x is going to be 6x plus 1. Don't forget your constant integration. Now at this point the question's basically cheering you on, saying you're on the right tracks, because we end up with this lovely bit of cancelling here. Okay, if we didn't end up with this cancelling, we would end up with a function that we wouldn't differentiate by the chain rule. When we're using this method, we should end up with a final answer, which is something we would differentiate using the chain rule. So because these 6x plus 1s cancel each other out, that's telling me you're on the right tracks. Okay, so then we're going to have 2 lots of 3x squared plus x all cubed plus c, which is what we started with. So we had something here which we differentiated using the chain rule to get something written in this form. When we integrated it, we've spotted it's in that form, k f dash of x, f of x to the power of n. We've then used that reverse chain rule to get back to where we started. Okay, so that's one of those forms that we can use to one of these forms that we can kind of spot and then use this idea of adding 1 to the power, divide by the new power, multiplied by the derivative of the inner function. Okay, let's move on then. So what about if we've got some exponentials going on? So again, let's take a similar kind of tack. So what we're going to do is we're going to start off by doing some differentiation and then see if we can figure out the steps and then reverse that process. Okay, so if we have a look here, we've got 2e to the power of sine x. So if I want to differentiate that using the chain rule, I've kind of got my big function, which is 2 lots of e to the something. Now we know that the derivative of e to the x is just e to the x, so if I differentiate 2e to the something, it's just going to remain as 2e to that something. Okay, what I now need to do is I now need to multiply by the derivative of the inner function. So in this case, our inner function is sine x, and when we differentiate sine x, we get cosine of x. So again, just tidying up what we've got, we'd have 2 cos x e to the power of sine x. So the same as last time, what we want to do is we want to look at this answer and think about what's special about kind of the form of this answer that's going to give me a hint that what I'm dealing with is a function that's being differentiated using the chain rule. So if we have a look at this function, what we've got is we've got the sine x is what's being preserved, so let's call that f of x. So we've got e to the power of f of x, and then in front of it we've got a constant multiplying the derivative. So we've got k f dash of x here. So we've got k f dash of x e to the power of f of x. Okay, so let's see if we get a similar kind of form when we differentiate this. So if we start differentiating this one, we've got dy dx. Okay, and then my big function is 3 lots of e to the power of something. So when we differentiate that, we're left with 3 lots of e to the power of something. Okay, we then need to multiply that because of the chain rule. We need to multiply that by the derivative of my inner function. Now my inner function is x squared plus x. So when we differentiate that, we're going to get 2x plus 1. Okay, so again, tidy up time. Just tidy things up a bit. We're going to have 3 lots of 2x plus 1. E to the power of x squared plus x. So if we look at what's the same from where we started to where we ended up, well, we've still got the inner function being preserved again, haven't we? So we've got it in this form where we've got e to the power of f of x, and then in front of it I've got a multiple of the derivative of that inner function. So I've got k f dash of x, exactly the same kind of thing. Now, of course, when we're trying to spot this form, it may be that whoever's differentiated this to give us our function we're going to integrate, they may have multiplied this bracket back in and got obviously 6x plus 3, but it's still written in that form. We might have to think about it a little bit more for a little bit longer, but it's exactly the same kind of thing. Okay, so same as last time, what we want to do is we kind of want to undo these steps. So a function that we spot that's written in this form, if we want to integrate it, we want to kind of reverse this process. So again, if we've got something that's written in this form where we've got k f dash of x e to the power of f of x, we want to integrate that with respect to x, basically we leave the function alone. Okay, if we have a look at what we've got here, kind of when we differentiated, we ended up with the answer being replicated. There was something else going on, but you know, we've still got the 3 and the e to the power of blah here. We've still got the 2 and the e to the power of sine x here. So that's been preserved. So actually when we go to integrate this, we leave it alone. Now the thing that's changed is we've ended up with the derivative of the inner function. So if we want to undo that, we want to divide by the derivative of the inner function. And then don't forget your constant integration. So we've ended up dividing, basically leave everything alone, divide by derivative of the inner function. Now if for a moment we just go back to what we did a moment ago, you can see that this is becoming a bit of a common theme. We're dividing by the derivative of the inner function. When we had this kind of polynomial form, we were also having to divide by the new power, but we were dividing by the derivative of the inner function. When we look at what we've got here, slightly different setup, it's an exponential function this time, but we're still dividing by the derivative of the inner function. That's a common theme throughout all the things we're looking at today. We end up dividing by the derivative of the inner function. So same as last time, let's take these answers now, try and apply this method and see if we get back to where we started. So if we have a look at this first one, we want to integrate 2 cos x e to the power of sine x dx. When we integrate this, what I said was leave it alone, don't do anything to it. 2 cos x e to the sine x. And then we divide by the derivative of the inner function. My inner function is sine x. The derivative of the inner function, therefore, is cosine of x. And we end up with plus c. And the same as with the previous examples, we then end up with the functions cancelling down. That's the function telling me you're on the right tracks. Okay, you've not made an error here. And we've ended up with what we started with when we differentiated, so we've reversed the chain rule. Okay. The fact that we end up with something that we could check by differentiation with the chain rule tells me I've not done anything too horrendously wrong. So let's just check this next one. So if we integrate 3 lots of 2x plus 1 e to the power of x squared plus x dx. So again, leave it alone. Don't do anything to it. All we need to do is divide by the derivative of the inner function. Our inner function is x squared plus x. So when we differentiate that, we get the 2x plus 1. That's what we're going to divide by. Don't forget your constant of integration. And same as before, the question's basically giving me a pat on the back and saying I've got it right, because we end up cancelling things down. If you end up where it's not cancelling down, either you've made a mistake somewhere or this wasn't the right method to use in the first place. So if things don't cancel down a little bit, you don't end up with something that you could differentiate with the chain rule to check your answer, then you've gone wrong. Okay. Okay, let's keep on going. So we've done some kind of polynomial-ish. We've had a bit of trig going on, so now we've got some natural logs. Okay. So we hopefully you'll know the drill by now. What we're going to start off by doing is we're going to start off by doing some differentiation, try and figure out what's going on, try and figure out the steps so I can undo those steps. So using the chain rule, I'm going to differentiate each of these. I know I'm using the chain rule because it's a function within a function. So my outer function is excuse me, is 10 lots of log of something. Don't care what that inner function is at the moment. And hopefully we know that when we differentiate natural log of something, we get 1 over something. So because we've got 10 lots of it, we're going to have 10 over the something, which happens to be 2x minus 1. And then we multiply that by the derivative of our inner function. Now our inner function is 2x minus 1. So the derivative of that is 2. So what we end up with is 20 over 2x minus 1. It's possibly a little bit tricky here to kind of figure out what's special about this form. So let's have a look at the next one and then see if we can spot what kind of form we're looking for when we're trying to kind of reverse this process, or to spot that we need to reverse this process, if you like. So if we have a look at the next one, dy dx, again, I've got a function within a function. I've got this polynomial within my log function, so I know I'm using the chain rule to differentiate here. So my outer function is just 2 lots of log of something or other. So when I differentiate that, I'm going to get 2 over that something or other. And then we multiply that by the derivative of our inner function. Our inner function here is 3x squared plus 1, so the derivative of that is going to be 6x. So then if we tidy that all up, I'm going to get 12x over 3x squared plus 1. So what we were trying to spot was, well, what kind of form are we getting? When we differentiate with the chain rule, a log function, a natural log function, what kind of answers are we getting? Now the key to spot here is I had a linear function down here and then just a constant in the numerator. Down here I've had a simple quadratic and then a simple linear function. It isn't the exact derivative in both cases, but it is a multiple. So the form we're looking for in this case is we've got our inner function in both cases is being preserved in the denominator. So we're going to have f of x in the denominator, and then in our numerator we've got a multiple of the derivative of that inner function. Now both of these kind of conform to that form. So this is another one of these key forms we're looking out for. We're trying to spot in functions we've been asked to integrate, because we can say, aha, that's something I can kind of reverse the chain rule on. So in general, if we have a function that's written in this form, and we want to integrate it, if we kind of look at what's going on, that denominator is within your log function. Okay, so we're going to leave the numerator alone, and then whatever's in the denominator is what goes in my natural log function. Okay, and then you'll be sick of me saying it by now, we divide by the derivative of that inner function. And hopefully when we apply this, what we'll see is those derivatives of the derivative of the inner function in our denominator will cancel with part of the numerator. Okay, so if we apply that idea, just to check these results, kind of reverse what we've done with our differentiation. So if we integrate 20 over 2x minus 1, we spot it's in that form and go, aha, that's going to give me a natural log because I've got a multiple of the derivative of the denominator in the numerator. I'm going to leave the numerator alone. I'm going to put my denominator in the natural log function, and then I'm going to divide by the derivative of the inner function, so divide by the derivative of 2x minus 1, which is 2. So in terms of things cancelling down, we then end up with, well, the 20 divided by 2 is just going to give me 10. So I'm going to have 10 ln 2x minus 1, yippee. Okay, so let's just check this other one. So this time we're integrating 12x over 3x squared plus 1 dx. So I'm going to leave the numerator alone. I'm going to put the denominator in my log function, and then I divide by the derivative of the inner function. So the derivative of my inner function here is 6x. Don't forget plus c. The x's cancel, and the 12 divided by 6 is going to give me that 2, isn't it? So I'm going to end up with 2 ln 3x squared plus 1 plus c. And you can see that we've kind of been able to reverse that chain rule. Okay, so if we just kind of recap, we've kind of spotted 3 main forms there. Okay, so we've got this form here, where we've got a multiple of the derivative of the denominator in the numerator. When we integrate something of this form, we're going to end up with a log function. We've got the function involving, the form involving exponentials, where we've got e to the power of a function and a multiple of the derivative at the front. Okay, where basically we just divide by the derivative of the inner function. We've then got the other one, the first one we looked at, where we've got a function being raised to a power and the multiple of the derivative of that inner function at the front, where we'd add 1 to the power and then divide by a derivative of the inner function. What the 3 things have in common is that each time we would be, we might be doing a little bit of something else as well, but we're dividing by a derivative of the inner function. So you need to be able to identify those forms. So if we have a look now just at a mixture of questions, what we should be aiming to do if we're asked to iterate something is, first of all, try and identify if it's in one of those 3 forms, and if it is, we can reverse the chain rule. So if we have a look at this first one, hopefully it's reasonably clear to see what I've got is I've got a function being raised to a power. Now the function I've got here is a simple quadratic, and I've got a very simple linear function at the front. So we can see that this is in the form, we've got a function being raised to a power, and then in front of that we've got a multiple of the derivative of that function, so k f dash of x. Okay, so I've spotted that it's in that form, so I know I can reverse the chain rule. So to reverse the chain rule, I add 1 onto the power, leave everything alone. The only thing I change is I add 1 onto the power, so it becomes 6, and then divide by that new power multiplied by the derivative of the inner function. So the derivative of the inner function here is going to be 6x have plus c, and then it's just a case of tidying up. The x is cancelled. That's the question saying, yippee, you're on the right tracks, keep on going. Okay, then we just need to tidy up 4 over 36, which is a ninth. So we end up with 1 over 9, 3x squared plus 1 to the power of 6 plus c. At this point, we should be thinking, seeing as I've used the reversing the chain rule method, is this something I would differentiate using the chain rule? Yes, it is. Okay, so we've got the x's cancelling that tell me I'm on the right tracks. I've ended up with an answer that I could differentiate using the chain rule to check my answer. You know, it's looking good. Let's have a look at this one next. So if we have a look at this one, we've got our 6x in our numerator and an x squared plus 1 in the denominator. So if we think about what we've got going on here, we've got a function in our denominator, and then we've got a multiple of the derivative of that denominator up in our numerator. So this is an example of one that's going to give us a natural logarithm. So if we start integrating that one, we're going to get, leave the numerator alone, chuck the denominator in the natural log function, and then divide by the derivative of that inner function, which is 2x. Oh look, the question's telling me I'm on the right tracks because the x's are cancelling, and the 6 over 2 is just 3. So we have 3 ln x squared plus 1 plus c. Okay. Again, this is something I could differentiate using the chain rule to check my answer, so it's looking good. I've probably done the right thing. Let's have a look at this one next then. Okay, so if we have a look at this next one, trap people fall into is quite often they think, oh, there's a fraction there with some algebra going on, it must be one of those natural log ones. Be careful. If we look at our numerator here, it's a simple linear function. If we look at our denominator, we've got x squared plus 1 being squared. Okay, so if we multiplied this out, we'd actually get a quartic. We'd end up with something with the highest power being a power of 4. So if I differentiated that, I'd end up with a cubic. So I haven't got a multiple of the derivative of the denominator up in the numerator. So I can't, it's not in this form. I can't use this method. So what I need to do is I need to think about, well, is there something else I could do? So what I could do is I could just rewrite the function by bringing that denominator up. So don't assume just because you've got a fraction, it's going to be one of these natural loggy ones. Okay. If we look at that now, I've got a function being raised to a power, and then it's a quadratic here, linear function here, so I've got a multiple of the derivative of that inner function at the front. So it's in this form up here. So using the same method, I'm going to leave everything alone, just add 1 onto the power. Then we divide by that new power, multiply by the derivative of the inner function. Again, things are cancelling down nicely. Okay. So our final answer will just be minus 1 lot, because the 2's will also cancel. So we'll just end up with minus 1 lot of x squared plus 1 to the power of minus 1 plus c. So you could rearrange that, have it as minus 1 over x squared plus 1 if you wanted. That might be a slightly nicer way of writing that answer. Okay, but we've ended up with something that we could differentiate using the chain rule to check our answer. Okay, and then the last one, before you can stop listening to me. So if we have a look at what we've got going on here, we've got our exponential in the power, we've got a function, and at the front we've got a multiple of the derivative of that. So it's in this function where we've got k f dash of x e to the power of f of x. So basically, remember, for integrating this, we leave it alone. We don't do anything to it to start off with. We leave it alone, and then we just have to divide by the derivative of the inner function. So our inner function is x squared plus 1. Derivative of that inner function is 2x. Oh look, things are cancelling down for us. That's, you know, a pretty strong indication we're on the right tracks. We end up with 3 over 2 e to the power of x squared plus 1 plus c, and we're done. Okay, so hopefully that's made sense. Obviously you can go back and go over any parts you need to go over again if you're unsure about anything. What I strongly recommend you do now is go to page 206 in your textbook. I would have a go at this column here, so part 1 of each part of question 1a through to I. Some of these are quite challenging, but they all do fall into those forms we've gone through today. Okay, so I'd have a go at all of those. If you're working at home and you get stuck on any of those and you need a little hint as to where to get started on some of them, then do drop me a message on the VLE. So I'd have a go at those, and if you want a little bit of a challenge, you could maybe have a look at question 2, and then question 5, which is on page 207, also looks fun. Okay, and then question 6 looks very fun. So there's something there to keep you busy for a while. Okay, so hopefully that's been useful. If it hasn't, or if you get stuck, just drop me a message on the VLE or to my school email, and I'll get back to you as soon as I can.